Hey everyone, and welcome back to another deep dive. Today we are immersing ourselves in a world of grease, steel, and absolute mechanical magic. We're talking all about automotive clutches. Whether you're a gearhead who loves that tactile, purely mechanical thrill of a manual transmission, or you just want to know what exactly is happening under the floorboards when your automatic car shifts seamlessly on the highway, well, you are in the exact right place. This explainer is going to take all that complex engineering and break it down into something you can literally almost feel in your own hands. Okay, let's dive into this. Here is our roadmap for today. 1. The engine power dilemma. 2. Anatomy of the clutch. 3. Hydraulic and automatic systems. And finally, 4. Signs of clutch failure. Section 1. The engine power dilemma. To really understand why a clutch even exists, we first have to tackle a fundamental physics problem. Think about this highly relatable, real-world driving scenario. How do you stop your car at a red light without the engine just completely dying? You see, an internal combustion engine has a pretty limited torque band, which means it needs to be constantly spinning to stay alive and generate power. If your wheels stop and your engine is permanently rigidly connected to those wheels, well, the engine is forced to stop too. It stalls. You absolutely need a temporary bridge between that spinning engine and those stationary wheels. And that bridge? That's the clutch. By definition, it's a mechanical device used to engage and disengage power transmission between a running engine and a gearbox. And the whole secret here comes down to one word: friction. Imagine rubbing your hands together lightly. They slide past each other super easily, right? Now press them together as hard as you possibly can and try to slide them. They lock up. That clamping force is exactly how a clutch works. It uses massive pressure and high-friction materials to grab onto the engine's power and send it to the wheels, or, just as importantly, let it slip away when you need to come to a stop. Section 2, Anatomy of the clutch. Let's pull back the metal housing and take a cinematic look at the big three components that make all this friction possible. First up, we've got the flywheel. This is basically the foundation of the whole system. It bolts directly to the engine's crankshaft, which means it is constantly spinning the entire time the engine is running. It's this incredibly heavy metal disc, and the face of it is precision machined out of iron. Now, why iron? Because it wears unbelievably well and it dissipates the absolute massive amount of heat generated by all that friction. This iron face essentially acts as the mounting surface for the rest of the clutch system. Next up is the pressure plate, and this is the muscle of the operation. It bolts straight to the flywheel, completely sandwiching the clutch disc right in between them. In a coil spring pressure plate, you have these small, heavy-duty coil springs that honestly look a lot like engine valve springs. These springs are constantly, violently pushing a large, flat metal ring against the clutch disc, forcing it right into that spinning flywheel to engage the system. But if you drive a modern manual car, you're most likely dealing with a diaphragm pressure plate. Instead of a bunch of individual coil springs, it uses one large flexing metal disc. It kind of looks like a shallow bowl with all these metal fingers pointing right toward the center. When you press the clutch pedal with your foot, a bearing pushes exactly on the intersection of those fingers. It's a totally brilliant lever system. You press the center in, it pivots, the outer rim pulls out, that massive clamping force vanishes, and the power flow is instantly interrupted so you can safely shift gears. So, if we put it all together, the power flow works in 4 clear steps. The engine crankshaft turns the flywheel. When the clutch is engaged, the pressure plate jams the stationary clutch disc against that spinning flywheel. The disc then begins to spin, which turns the transmission input shaft, finally sending all that power down to your wheels. But here is an amazing little detail. If that connection was completely rigid, your car would violently jerk every single time you shifted. To prevent this, the clutch disc has these small torsion springs built right into its center hub. They compress just enough to absorb the shock and vibration of the engine, making sure the power transfer is perfectly smooth. Section 3, Hydraulic and Automatic Systems. We've talked about the mechanical clamping, but how does your left foot actually move that incredibly heavy pressure plate? And what happens when a computer takes over? Older or simpler setups use a traditional mechanical linkage, literally a steel cable directly connecting your pedal to the clutch fork. But as you can imagine, cables stretch, they bind up, and they require a pretty heavy leg effort. Contrast that with a hydraulic system. Just like the brakes on your car, this uses fluid dynamics to transfer the force. It's so much smoother, it requires way less physical effort, and it actually self-adjusts as the clutch naturally wears down over time. This hydraulic system relies entirely on 2 main components. When you step on the pedal, you're actually pushing a piston inside what's called the master cylinder. That translates the physical pressure from your foot into hydraulic fluid pressure. That highly pressurized fluid then travels down a line to the slave cylinder, which sits right next to the transmission. The fluid forces the slave cylinder to extend out, pushing the clutch fork, which then presses that diaphragm spring we talked about earlier. It's literally fluid power doing all the heavy lifting for you. Now, standard car clutches are what we call dry clutches because they are cooled purely by the surrounding air. But what if you're riding a high-revving motorcycle or driving a massive 1,000 horsepower hypercar? You're going to need a wet clutch. A wet clutch is completely immersed in cooling, lubricating fluid. But because oil obviously makes things super slippery, a single disc would just spin out and slip. So wet clutches use multiple stacked plates to drastically increase the surface area. The oil absorbs the immense heat generated by the friction, which actually means a well-maintained wet clutch can sometimes last the entire lifespan of the machine. And here is what that same concept looks like tucked inside an automatic transmission. You might not have a clutch pedal, but make no mistake, you absolutely still have clutches. A multiple disc clutch uses a dense stack of alternating steel plates and friction plates. When the automatic transmission decides it's time for a shift, a hydraulic piston forcefully squeezes this entire stack together, instantly locking them into one solid unit. And this brilliantly illustrates why those multiple disc clutches are so critical. Automatic transmissions rely on planetary gear sets. These are really complex arrangements of sun gears, planet gears, and ring gears. By using multiple disc clutches to instantly lock and unlock different parts of those gear sets, the transmission can automatically change gear ratios based on your speed and engine load, all without you ever lifting a finger. Taking automation to the absolute extreme, we have the dual clutch transmission, or DCT. Think of a DCT not as your standard automatic, but literally as two separate manual transmissions stuffed into a single housing. One clutch handles all the odd gears, first, third, fifth, while the second clutch is entirely responsible for the even gears. So when you're accelerating in first gear, that second clutch is already pre-selected second gear and is just waiting for the computer's signal to swap. The shift happens in milliseconds. It eliminates the need for a sluggish torque converter and delivers lightning-fast, perfectly seamless power. Section 4. Signs of clutch failure. Now that we know how beautifully all these parts work together in harmony, let's do a quick, practical autopsy on what happens when they finally break down. Because let's face it, eventually, friction takes its toll on everything. The good news is your clutch will almost always warn you before it completely gives up the ghost. If your pedal suddenly feels spongy or just too soft, you're probably looking at a hydraulic leak or air trapped in the lines. If you start noticing a harsh, really acrid burning smell, that is the friction material on the clutch disc literally burning up from excessive heat. Also listen for abnormal noises. A squeak when you press the pedal is often a dry release bearing, while a heavy, clunky rattle when you're just sitting in neutral could mean broken torsion springs on the disc itself. And if your pedal sticks right to the floor and won't come back up, stop driving. Your release mechanism has officially failed entirely. Two of the most common mechanical headaches you'll run into are slipping and grabbing. Slipping is exactly what it sounds like. You step on the gas, the engine just revs aggressively, but your car barely speeds up at all. The pressure plate simply can't hold the worn-out disc against the flywheel anymore, or maybe the disc got contaminated with leaking engine oil. On the flip side, grabbing is when the car violently jerks and shudders when you try to accelerate from a dead stop. This isn't a loss of friction, it's uneven friction. It's usually caused by a warped flywheel, a damaged pressure plate, or broken springs inside the housing. Then we have dragging and pulsation. A dragging clutch just flat out refuses to fully disengage. You push the pedal right to the floor, but the disc keeps touching that spinning flywheel. So when you try to shift, you'll hear an awful grinding noise because the transmission is still receiving power. Pedal pulsation, on the other hand, is a purely tactile warning. If you rest your foot lightly on the pedal and feel a rapid throbbing or vibration, something inside that rotating assembly is wobbling. Usually, the engine and transmission have become misaligned, or the flywheel is warped, and that runout vibration is traveling right up the hydraulic fluid directly into your foot. So after all that, how long should this incredible mechanical system actually last? Well, depending on your environment and how you drive, the average lifespan of a typical automotive clutch is anywhere from 50,000 to 150,000 miles. That is a massive range, right? And the difference almost entirely comes down to the driver. If you want to push that lifespan all the way to 150,000 miles, here is exactly what you need to do. First, avoid riding the clutch. Never, ever rest your foot on the pedal while you're driving. Even the slightest pressure can cause that release bearing to ride against the diaphragm spring, which creates entirely unnecessary heat and wear. Also, never use the clutch to hold your car in place on a steep hill. That's what your brakes are for. Make sure to keep an eye on your hydraulic fluid levels in the master cylinder reservoir, just like you would with your brake fluid. And if your pedal ever starts engaging too high or too low, get it adjusted right away to prevent any permanent damage to the disc. We've covered the physics, the heavy-duty anatomy, the incredibly clever hydraulics, and the telltale signs of wear. It really is a stunning piece of engineering that so many of us interact with every single day without a second thought. So I'll leave you with this. Next time you pull out of your driveway, shift into drive, or press down on that left pedal, will you feel the mechanical symphony of friction, fluid, and steel happening right beneath your feet? Thanks for joining me on this explainer, and keep learning.